This is a presentation on the new features within Alphacam 2017 R1. This presentation will look at the enhancements and modifications we've made to the machining options. So we've already been looking at some 3D machining options regarding the changes to the machining dialogues. And you may have noticed that there are only some strategies available. Well, at the moment this is what we call a work in progress. As development are updating the features and the dialogues, rather than waiting till we've done every single strategy, because there are so many strategies, we've decided to release the ones that we've done so far rather than holding back, so users can get the benefit of these new strategies straight away. As the message says at the top of the dialog, if any command isn't in the 3D machining that you require, the 3D solid and the 3D surface machining commands are still there, so you are still able to use these. In the previous version of Alphacam, if you just wanted to machine a particular area on a solid and work with STL as well, you had to select the whole solid and the STL and then restrict the area that you wanted by using a boundary. Now this would give you the machining that you wanted, but obviously there was processing time involved because the whole solid had to be selected and analysed. In this version we're now able to select individual solid model faces and STL, and also a boundary can be used to still restrict the machining where required, but this will speed up the processing time as the whole solid does not have to be analysed. We've seen some of cylindrical parallel in the GUI modifications, and we obviously saw the extents visualization. But now regarding machining options, we now have the option regarding width of cut, where you can specify an actual value. So we see on the main dialog that we have the width of cut in degrees. Well, if it's easier for the user to actually say, well, I want a particular step over, this will then calculate the width of cut in degrees. And if you click the button on the end of the width of cut degrees dialog, it will bring up the calculate width of cut dialog, where you can specify an actual chord length and the effective diameter of that chord length. So you specify the step over that you require, and then the system will calculate the actual width of cut in degrees that is required to give you that step over. Regarding the rough and finish command, we've now introduced a breakout cut option. This is available in the router and the stone modules, and what this basically does is you specify a distance and it will put a cut on the exit edge of the feature that you're cutting to basically try and avoid any breakout in wood or any chip out in a stone product. So it just takes the tool in the opposite direction just to remove that material, so when the main cut comes through it hopefully shouldn't cause any breakout. In the stone product, we've made enhancements to cut with disc. We saw a little bit of this on the presentation once again for the GUI with showing the actual shape of the part. So we're getting on-screen feedback. It's actually rendering the geometry that's going to be cut. Also the profile to be cut. Not only can you draw the profile in your drawing, you can also have a profile library, and that will bring up or open a folder of the profiles that you can create yourself and then save away for use at a later date. There are some profiles provided with the system as examples. Also in the stone product, we've got the option for cut holes. When we're cutting holes in stone, generally core drills are used. So as we can see, that's not a solid drill, it's basically just going to cut a section out, a thin section, that will leave a slug in the middle. Well, that slug needs to be removed before that drill can be used again. So there's now an option on the dialog to eject the slug. So when the drill's finished, the slug can be ejected. Also an option to modify the feed rate. So when it's about to exit the part at the bottom of the hole, we can slow the feed rate down just to avoid any chip out at the bottom. Looking at the drilling command, we've made some enhancements to control the depth of holes. And basically, if you are using feature extraction and this gives you the bottom of the hole, your drill may or may not match the actual cone angle of the feature that's been extracted. So on Auto Z and feature holes, we now get additional options where we can look at basically matching the shoulder, matching the tip, and knowing if there's going to be a foul on the drill cone angle and the actual hole cone angle, and then we can adjust accordingly. So we're giving full control over exactly how the drill will be going to the correct depth that you require on the feature that you're doing. Now if we look at soaring, in the previous version the soaring had no concept of parts next to parts, so when you did saw cuts it was soaring in the entire geometries that were selected. Well, now if those geometries are selected in one operation, they will basically be analysed as part of the soaring cuts, and therefore the soaring cuts will be trimmed accordingly so that parts aren't fouled. This is what we call foul avoidance. And we can see on the image that basically those cuts are removed. This may mean that some parts will not be cut in their entirety, but this is much better than fouling parts because you can then go in with an additional tool and finish the part off. Also regarding soaring, we've introduced a command called Soaring Extensions. What this allows the user to do is basically extend saw cuts to boundaries or by certain distances, where it could be quite useful that you can extend the start of a saw cut out of a sheet of material, which avoids plunging actually into the material. If we now look at our lathe product, we've added an option for threading retract. What this allows the user to do is specify a rapid distance above the part for each threading return pass, so we know that we're moving to a safe distance away from the part for each retract. This is going to be more relevant for linear threading rather than can cycle, as the machine will usually be controlling this itself in the can cycle. Also in lathe, we saw this in a previous version for milling to basically auto update the material. Now when you're doing milling operations in lathe, you also have the option for auto update material. What this allows the system to do is look at previous machining operations and then make sure that we're not wasting areas of machining that have already been machined. So in the background the system will create a stock of what has previously been machined and then use this as the stock for the next Z-contour roughing machining operation. Now if we look at the configure option, in the machining area of configure we've added an option for residual contour pocket step over. So before we could specify width of cut of diameter for a contour pocket, but now for residual pocketing we can specify a separate width of cut value, which gives more control over our residual pocketing toolpaths. Let's have a look at these features now within Alphacam 2017 R1. Let's begin by looking at the Select Faces with STL option. So we can see here we have a rather large solid model, but we're only really interested in looking at this area here with the detail. So I just want to analyse this particular face and the STL feature rather than the whole solid model. So let's activate the work plane. And we can see we've got a boundary on here already. We can refresh this just to sharpen up the edges. Let's go to the machine menu and select a tool. I'm going to pick a 2mm ball end and we're going to go to 3D machining. So I'm going to remain 3-axis because it's in a work plane, so this will give us a 3+2 feature. And I'm going to pick the constant cusp strategy. I'm going to use boundaries and also select faces. Say OK to that, we get the message that the toolpaths will be in the work plane, and we're going to select the boundaries as prompted. We then have the machining dialog displayed, so we need to set our Z levels accordingly. I'm not going to change anything in the lead and lead out links. Machining data, we can obviously set the values for our quality of cut and values obviously coming off the tool. So let's say OK to that. Let's now go and pick the individual face and the STL feature, and we'll say finish and let the machining engine calculate the toolpaths. And we can see how quick that is, and that's the time saved with just analysing one face of the solid instead of the whole solid itself. Now we're going to look at the cylindrical parallel width of cut calculation option. So let's begin by selecting a tool and go to the 3D machining command. We're changing this to the YZ rotation again, and we're picking the cylindrical parallel strategy. Say OK to that. Pick the x-axis as the line of axis of revolution, and then pick the solid. So we can see our extents visualization. We'll look at that in a minute. Let's just check and set our Z levels. Not changing anything in lead in, lead out links, so we go to the machining data. So width of cut in degrees. I can specify an amount in degrees, but I actually want to set a specified step over amount. So I'm going to click the calculate width of cut button. So this brings up a new dialog where we now specify a width of cut as a chord length, so like a real step over amount. So I'm going to say 1. And we also need to specify the effective diameter. If I don't know what that is off the top of my head, I can get the information from the drawing. So I'm going to click the browse button, and I'm going to pick a point on the solid, and that will return the diameter for me. So let's say OK to that. And just so we're not sitting here watching the calculation for a long time, I'm going to change the end angle to 5, and then I'm also going to restrict my Z levels. So I'll make the maximum of 10 and a minimum of 0. I'm not going to change anything with the tooling data, so we'll say OK to that, and we'll let the toolpath calculate. So now we can see that we've told the system we want a 1 mil step between paths, so let's just go and check that's what we've got. If I go to distance angle and look at the endpoint of this element to the endpoint of this element, I can see that the distance is 1 mil as I've requested. Now let's look at the option we've built into the rough finish command for breakout cuts. So we can see I've got a profile here with a toolpath on it. If we just run the simulation and have a look at what that's doing, we can see we get a standard rough finish cut moving along, which is fine. At the other end it's going to come out. And our concern here is that on this far end, going with the grain, that basically we'll get some breakout on the wood here. So this is what we want to try and avoid. So if I turn the simulation off, and let's go and edit the toolpath. So if I now come to edit, we can see we have this option for auto breakout cut. So let's select that and set a length of 20 millimeters. So that will be the length of the breakout cut along the profile. So we now say OK to that, and we can see that we have this additional toolpath added now. So if we just watch that in the simulation again, and let's see what that does. So it makes the breakout cut, and it then goes over the other side and completes the normal toolpath. The lead in and lead out on the breakout cut used are the same as have been applied for the main toolpath. And this also works with compensation. So if I list the NC code, list it all, we can see on the first cut we have our rapid deposition, and then we have a G42 for compensation to the right, and then after it's made that cut, wrap it up, move to the new position, and then it does a G41 to cut to the left for the other part of the profile. Now we're going to look at the cut with disc command. So let's start by selecting a tool. That's my disc tool, and now we go to cut with disc. So here's the new dialog. Obviously the tool selection here. We'll look at the strategy in a minute. The first thing we need to consider is the geometry and the profile. We can see the red crosses here, which means they haven't been selected, and that means I can't continue into any of the dialogues until they have been. So let's start by picking the geometry. Now we see the green tick, which means it is selected. We're able to reverse the direction if we require, or change the tool side to affect whether we're going to cut inside or outside of that geometry. I could now pick a profile if the profile I wanted to cut was drawn actually in the drawing. But as I don't have a profile in the drawing, I'm going to load one from the library. So if I click this, it browses to my profiles folder, and we can see the pre-drawn profiles that I have. So I'm going to select this profile here. We now see how it's rendered and shown on the drawing. And now as we change the settings regarding the profile, we can see how this changes what will be cut. So if I deselect attach at start point, it will put the geometry at the bottom of the profile. And I can then click flip, and that will give me the inverse. And then likewise I could click attach at start point again and give me the inverse with the geometry at the top. And deselect flip, we're back to where we were originally. We can also now see the strategy that I have horizontal, which will give me horizontal Z slices. If I change this to disk side, it will still cut the same profile, but the tool will move up and down in the Z axis to use the side of the disk to create the profile. So if we click vertical, we can now see how this actually changes the orientation of the disk. And once again, vertical with disk side will use the side of the tool. Normal to profile will be more obviously for a 5-axis machine where the disk can angle. I'm going to leave this set in horizontal and then move to levels and cuts. We can see we have applicable Z levels set regarding the size of the tool. What we have with our safe XY distance is if I change this value to a large value, we can see how the tool is dynamically moved to show where we will be starting. Therefore, if I change this to 5, we can see how much closer into the material we will be starting. Looking at the cuts, we can go bidirectional, and I'm going to do a finish pass only. I'm not going to change any of the other settings, and when we're happy with these values, I can click OK. Let the toolpath generate. So we get to see, here's our toolpath, it's created. If we run the simulation, we get to see how the disk's moving around and going in the bidirectional strategy that we requested. Now we're going to look at the additional options we've added to drilling within the stone module. So let's start by selecting a tool. So I'm going to go and select my core drill. If we open this tool and just rotate the drawing around, we can see that we've defined it as a solid tool, so it's actually got the shape of the core drill. So let's accept that and then go to cut holes. So we have the normal tool data. I'm going to go holes to match drill diameter, and we're going to output linear code. And if we go to the levels, I'm just going to put a bit of Z stock so we can basically go through the bottom. We now see we have the option to eject the slug. So if I select that, because I'm using the core drill, and also modify feed rate, so we just push out the bottom of the material a bit slower to avoid any chip out where possible. So let's just add that. Let's slow it down to 50% of the feed rate, and the distance from the bottom will do 5 millimeters, and that will be 5 millimeters from the final Z level. So as our material is 30 mil and we're going through 1 mil, it will actually start to change the feed rate at 26 millimeters deep. Happy with the tooling data set on the tool, so I'll say OK to that. We can select all, finish. It just finds the one hole of 35 millimeters. So just playing that in the simulation, we can now see our solid tool. And then we can look at the code. If we list all, we get to see where we start the drilling operation and we go to 26 mil deep at the full feed rate, and then we push through the bottom of the hole at the slower feed rate as specified. Now we're going to look at the drilling command and the changes we've made regarding control over drill depths relating to cone angle of the hole and cone angle of the drill. I'm just going to change this into wireframe so we can actually see the cone angle of the holes. So we've got this visible to us now. We can just refresh this to sharpen up the hole images. And what I'm going to do now is go to Solid Model Extract and go to Automatic Extraction. I'm not going to extract contours, just drillable holes and just in flatland. Say OK to that, so we can now see our holes have been extracted. What I'm now concentrating on is how this cone angle is going to be machined relating to the drill that we are using. So let's go and start by selecting a tool. And I'm going to begin by selecting a tool where the actual cone angle of the drill matches the cone angle of the hole. We can see that we have this, so I'm going to accept that. And let's go to Drill Machine Holes. And we're going to go Auto Z. Regarding here, I'm just going to select drilling and holes to match drill diameter, leave on can cycle. So the levels and the data, I'm drilling some blind holes, so I'm not going to set any stock amount. What we're looking at here are hole depths when you have Auto Z geometries, hole depths when we work with feature blind holes, and hole depths when we work with feature through holes, which gives the user complete control over the hole type that they're working with. As these have been feature extracted and they're blind holes, we're going to be concentrating on this dialog. I'm going to leave this on auto, which lets the system determine the best method of machining, which will avoid any fouling. So we'll say OK to that, select all the holes, say OK, and we can now see that the drill is shown as going to the depth of the hole. So if we just run the simulation and slow that down, we can see that the hole will go to the correct depth and the cone angle matches. So that's fine, that's exactly what I require. So let's just turn that operation off now and see what starts to happen when the cone angle doesn't match. So let's select a different tool. This time we're going to pick a flat bottom tool. So if I go to drill machine holes again, Auto Z, leave the value set exactly the same. So with auto, the system is going to do its best not to foul the hole, and we'll say all finish. And what we can now see when we run the simulation again is that the hole will now just go to the shoulder. It realizes it's a flat bottom tool, and if it went to the full depth it would foul the material. However, if I know the product that I'm making and I'm happy for that to do so, I can then control that. So if I edit the operation and come back to this, now what I want is to go to the full depth of the drill tip regardless of fouling. So I'm going to select drill tip and then say OK to that, and we can now see how the tool path has pushed through to the actual bottom of the hole. So let's just run the simulation again and we'll see that has happened. It goes past the shoulder and is now technically fouling, but if you're happy with that, then you have the control to do that. Now what happens if the cone angle doesn't match the other way? So let's turn that operation off and select a tool that has a smaller included angle. So we can now see that if this went to the full depth on the shoulder, it would foul through the bottom of the hole. So if we go drill machine holes, Auto Z, once again I'm going to leave this set to auto so the system determines the best method. Select all the holes, and we can now see that that has gone to the full depth of the hole, but in running the simulation we can see that it actually wouldn't machine to the hole shoulder depth, which we may require. What the user has the control here is to obviously go in and actually say, well, I'm happy to go deeper than that, and the foul is an OK situation. So if we edit that, what we can now say is that we're happy to go to the shoulder depth of the hole. So we say OK, and we now see actually how the tool path has pushed through deeper, but will give us the full shoulder depth. These are the changes we've made regarding changing the hole depths and the control the user has. Now we're going to look at the foul avoidance that's been built into 2017 R1. We can see on screen that we have three distinct parts actually on our sheet of material. I have an operation that I've actually created in 2016 R2, and if we go into the simulation and run this, we can see that the parts are cut, the saw cuts are in there. So the first part is okay, but due to the extensions on the parts, when we actually go to cut the other parts, we now find that we are cutting into our actual parts and therefore scrapping them. So how do we avoid this? Let's turn off the operation, and what I'm going to do now is just update this operation. What this will do is re-evaluate the geometries selected and the tool paths created using the 2017 R1 algorithm. So let's update this. We now get to see the big changes in the tool paths. And if we run the simulation again, we get to see how the saw paths are actually changed in reflection to the geometry selected so that none of them are fouled. And what this does actually require is that the operation, all the geometries are selected in one go. If they are selected separately, then they are not analysed in this way. Now we're going to look at the new command for Soaring Extensions. On the Machine tab, if I go to Edit Machining and then pick the Soaring Extensions command, we get to see a new dialog appear, and also we get to see Ghost Tools at the start point of each saw cut. Here are my options. I have Extend by Distance, which will just give me a basic extension on the tool path at the end that I click. Extend to Boundary, so we could pick something like the edge of the sheet and have the tool paths extend to that. Extend to a fixed point, or just reverse the direction of the saw cut. I also have a tick box here that will force the toolpath start to the extension. Basically, whichever end of the toolpath I click to extend is where it will then click the start point from. So let's just go for a basic extend by distance amount. I might say OK to that and click. We get a warning now basically saying that we're making an edit to the toolpath and it's part of an editable operation. But because we're making a change to the toolpath and not the operation, it will therefore lock the operation to stop it being edited. If we need to actually edit that operation afterwards, we would need to discard the toolpath edits, make the change to the operation and then reapply them. So I'm going to say OK to this, and we get to see the toolpath will extend. That's fine as a basic operation, but I might want to extend these toolpaths to the edge of the sheet. So if I press spacebar, that activates the last command, and I'm going to extend to the boundary. Well, this will extend exactly to the boundary, but I might actually want to overextend so the tool will plunge off the sheet. Get the option here to overextend by a certain amount. I'm going to go for 50mm, say OK, pick the boundary that we're going to extend to, finish that, and then pick the toolpath that we want to extend. So there we go, it goes to the edge of the sheet and overextends by a certain amount. And because I have Force Toolpath Start to the extension selected, when I click this here, it will change the start point and therefore adjust out accordingly. So I can do this on all of my toolpaths that are relevant. So we get to see the power of the Soaring Extensions command. Now we're going to look at the threading retract distance above part setting. So let's start by selecting a tool. Pick my threading tool, and I'm going to use spindle speed. So say OK to that. Let's now go to the turning work plane so we can see the geometries that we're going to cut with the threading tool. Pick the threading command. So we're going to pick our points on the geometry that we're going to cut from and to. Let's set our spindle speed. Happy with the other settings. We have some coolant. And I'm going to pick the thread data for a 20mm ISO thread. So these are the settings I have. These are OK. Number of starts 1. Acceleration distance we'll make 5. We'll do 8 passes with 2 spring passes. And now we see we have the rapid distance above part. So I'll set this value to 1. And we're going to lead in horizontally, lead out vertically. If we go to configure, we can confirm we want a right hand thread. We're going to cut down the flank and variable depth as longest line. Say OK to that. Enter in our approach rapids, and we can see we have our threading cuts here. So if I go to view display options, I can draw the toolpath rapids, and now I get to see the rapids for the retract. We can see that this is a setting of 1mm above the part. So if I just come and edit this operation, and let's change the retract value now to 5, say OK, and we can see how the rapids move up to be nice and safely away from the part. Now we're going to look at the auto update material settings within Lathe. If we just have a look, we already have our operations on here. We have our turning operations, and then we're spot drilling, drilling a hole, and then we're Z contour roughing this pocket out. If we watch that in the simulation, we get to see how it's currently going. So let's get the turning operations out of the way. So we spot the hole, drill it, and now we see that we start to rough this pocket. Well, this in itself is fine, except when it starts to now come into the hole, it's cutting in the hole, and this is basically cutting fresh air. So we need to try and remove this if we can. So let's stop the simulation and go, and we have our operations. We'll need to set a setting on the operation, but prior to doing that we need to make sure that our material is set for auto update. So I'm going to go find the material, and I'm going to click Set as Material, and this brings up the material setting dialog, and we see we have this tick box here for Associate for Auto Update. So I'm going to set that. There's no reason why you can't set that on the material when you define it in the first instance. So say OK to that. We now need to go and modify the operation as well. We edit the operation, and we can now see we have this setting here, auto update material from previous operations. So what this does is a background process where it runs a simulation of the existing operations and will modify the machining accordingly. However, it does only analyze milling operations. It doesn't analyze the turning operations within this. So let's set auto update material, click OK, and let the operation update. So now that's updated, let's go look at the simulation again, and we'll get to see how this has modified the machining. So we now see that the tool actually goes down the hole and it's not machining all the area inside it. It started within it and then works its way outwards. So we've removed all of that fresh air machining that was unnecessary.